Hello everyone, I am Namdev Kale from Department ENTC Engineering in KKWIEER College of Nasik. Did internship at Emertxe Information Technologies and presenting my project of micro oven simulation using PIC16F877A. In week 1, we were mastering C programming for embedded system. Proficiency in C programming is the foundation requirement for developing robust framework in the embedded applications. Fundamental data types. In the first week of internship was dedicated to mastering primary data types such as int, char, and float, which are used to store the manipulate numericals and character data within the microcontroller's memory. Control structures. We explored essential control flow mechanism including if-else statement and switch case blocks, which are critical for implementing decision-making logic in real-time systems. Modular code with functions. The curriculum emphasizes the use of functions to create modular, reusable, and readable code, facilitating easier debugging and system maintenance across complex projects. Memory management. Advanced topics such as arrays and pointers were introduced to manage memory efficiently, allowing for direct hardware manipulation and data storage optimization within constraints of PIC16F877A limited resources. Introduction to embedded system and architecture. An embedded system is specialized computing environment designed to execute dedicated tasks. What is the definition? Definition is an embedded system is a combination of hardware and software designed for specific function. Unlike general purpose computer, these systems are optimized for efficiency and cost, ensuring high readability and real-time performance in dedicated environments. What are core architecture? The basic structure of an embedded system consists of input sensor that gathers the data from the environment, a central processing unit or a microcontroller that processes the logic, and output actuator that perform physical actions based on the process information. What are the applications? Applications are common example of the system include domestic appliances like washing machine and air conditioners. These projects specifically focus on simulating the complex logic and timing sequence of a modern microwave oven. What is the difference between microprocessor and microcontroller? Microprocessor. A microprocessor serves a general purpose central processing unit, that is CPU. It lacks internal memory and peripherals, requirement external components like RAM, ROM, and input-output controllers to function. It is typically used in high-performance systems like laptops and workstations, where processing power is primary requirement. And what is microcontrollers? A microcontroller is often referred as a system on a chip, SoC. It integrates the CPU, memory that is RAM and ROM, and various input-output peripherals on a single silicon chip. This integrates allow for a compact design and direct control over hardware components. What are embedded advantage? Because of its integrated nature, the MCU, that is microcontroller, is efficient, cost-effective, compact, and energy efficient. This makes it the ideal choice for dedicated embedded applications like PIC16F877A using this microcontroller over simulation of this project. Understanding about this microcontroller hardware overview, the PIC16F877A. The PIC16F877 is a versatile 8-bit RISC microcontroller widely used in automation and education. Architecture and speed operates at the 20 megahertz with a RISC core that allows most instructions to complete in a single cycle. Input-output capabilities provide 33 programmable input-output pins across 5 ports for connecting keypads, displays, and sensors. Internal peripherals include in timer 0, 1, 2 for precise timing and a 10-bit ADC with 8 channels for analog inputs. Memory profile features 8K word of flash for code and 256 bytes of EEPROM for non-volatile data. Here is the diagram. Uh, Here is the architecture of PIC16F877. Software development and simulation environment. What are the softwares that we are using to build this project? First is MPLAB XID. This is official integrated development environment provided by Microchip. It serves as a primary workspace for writing, editing, and managing the embedded C source code. It provides essential features like syntax highlighting, project management, and integrated debugging tool that allow developers to step through code and monitor register values in real time. Second software is XC8 compiler. The XC8 compiler is a specialized tool used to translate high-level C code into machine-readable .hex files. This compilation process converts human-readable logic into specific binary instruction that the PIC16F877A microcontroller's hardware can understand and execute. It also performs code optimization to ensure the firmware fits within the device limited memory. And third is PIC Lab. In the absence of physical hardware, PIC Lab provides a comprehensive virtual development board environment. It allows for the real-time simulation of peripheral behaviors such as LCD displays, keyboard, keypads, and motors. This enables the testing of code logic and timing accuracy without the risk of cost associated with physical hardware prototyping. Project objective microwave oven control logic. The project aims to replicate the operational modes and safety features of modern microwave oven through software simulation. The primary goal was to design and simulate the control logic for a microwave oven using the PIC16F877A, focusing on user interface, design, and timing accuracy to ensure a realistic appliance experience. Operational mode. The system supports multiple cooking modes, including micro, grill, conventional, and start or quick start. Each mode is programmed within specific power levels and timing logic to simulate different cooking requirements. User interface. Users can select modes and set cooking duration via matrix keypad. All status, updates, prompts, and countdown timers are displayed on a character LCD to provide a clear feedback during operation. Hardware simulation. The heating process is simulated using a DC motor, which represents the cooling fan and magnetron. The motor activates the moment a cooking cycle starts and automatically stops upon completion or when paused. Display and user input mechanism. First is CLCD interface. A 16 into 4 character liquid crystal display is used to for user interface. It operates in 8-bit mode using register select RES pin to distinguish between control command and display data. This component is a crucial for providing real-time feedback such as the remaining cooking time and current mode status. Tactile switches. Individual tactile switches are used in the basic input like start and stop. These are configured with pull-up register, meaning the pin read high by default and low only when bottom is pressed. Software debouncing to prevent ghost presses caused by mechanical vibration. A software delay is implementation to ensure each key is registered only once, maintaining the system stability. And there is a matrix keyboard for numerical entry, a matrix keyboard is used. A microcontroller scans the grid by pulling rows low and checking column status. This efficient technique allows the system to handle multiple buttons while using a minimal number of input-output pins on the PIC16F877A. Timing logic and interrupt serving routes ISR. Timer2 configuration. In this project, Timer2 is configured to generate a precise 1 second interrupt. This achieved by setting the appropriate prescaler and postscaler values to divide the internal clock frequency. This period signal serves as a fundamental time base for the entire system, ensuring that the cooking countdown is accurate and consistent. Hardware timing. Unlike software-based delays, while which block the CPU, hardware timers run independently, allowing the microcontroller to perform other tasks while waiting for the next timing event. ISR, Interrupt Service Router. The ISR is a specialized function that executes automatically whenever a timer to overflow occurs. It handles the countdown logic in background, independent of the main programming loop. This ensures that the time is decremented exactly every second, regardless of what other processing the system is performing. System responsiveness. By using interrupts for timing, the main program remains free to monitor the stop or pause button on the keypad. This architecture ensures that the system remains responsive to user commands at all times, allowing for immediate intervention even while the cooking timer is actively running. Actuators and audio-visual feedbacks. The cooling fan, DC motor. In this simulation, a DC motor used to represent the microwave's magnetron and internal cooling system. The motor is programmed to turn on the moment cooking cycle starts, simulating the activation of the heating element. It is designed to turn off automatically when the timer reaches zero or if the user presses stop, ensuring a realistic simulation of appliance behavior. Audio feedback buzzer. A piezo buzzer is integrated into the system to provide essential audio cues to the user. A short beep is generated to confirm each successful key press on the matrix keypad. Furthermore, a continuous alarm is triggered to signal time up when the cooking process is finished, alerting the user that the operation is completed. Visual status update. The CLCD continuously updates the remaining time and current state, such as cooking, pause, or set time, providing the user with real-time visual feedback throughout the entire operation. Conclusion and learning outputs. Summary of achievement. The project successfully demonstrated a functional microwave oven simulating integrating keypad input, LCD output, and precise timer-based control logic to replicate real-world appliance behavior. Technical skill gain. I develop hands-on expertise in configuring PIC16F877A peripherals, writing efficient interrupt serving route, and debugging complex firmware using MP, LabX, and PICSIM for the environment and the simulation. Conceptual growth. The project reinforces the importance of structured programming and real-time responsiveness in embedded system design, highlighting how hardware and software must work in perfect synchronization. What are the future scope? The simulation could be further enhanced by adding a door open sensor interrupt and relay interface to control actual AC load in physical prototype, moving from simulation to real world product. Let's start with what we have done in our codes. Let's open mpxid. Here is the main.c file where our all the functions are written. Like let me open see here. See here are the four modes. For we have used all the concept like if else taught in our lectures. First is we have first mode as grill, second is conceptual, first is micro, second is grill, third is conventional, and fourth is start, and all are defined in if else statement. If else statement, and here are all the source files that we are using here. Here are header files where we have declared everything. Let's go to CLCD. Here is a code. We have used here timer 2 as we have discussed in the PPT. Let's move to the simulation in Pixim Lab. Let's load our hex file here. Powering on micro. See, all the four modes are looking like micro, grill, conventional, and start. Let's start with the first micro mode. When we click 1, the power is shown as 900 watt, and we have to set the timer. Let's set it as like 15 seconds. And we have like for example, let me show you that it is clear. Every function is working. And let's start with 15 seconds and enter. See, the fan is moving and our system has started. There are options like we can start or resume, we can pause, or we can stop it. But let's stop this and move to the next one. Cooking timer. Okay. Second function is grill. Now let's start the second one. And here also we have to set the time, like let's set it 20 seconds. Oh, sorry, 20 seconds. Now let me show you that all the functions are working. Now, if I click on pause, the time will pause. See, the time has been paused. And if you want to start or resume it, we can click 4 and it will start again. And to stop this, we can click on 6. But let us stop this and move to conventional. We have to click 3 for conventional. And here we have to set the degree Celsius, how much temperature we need. Like let's say it is 120 and enter. Now it will take the preheating time, like it is required 180 second. If is temperature is more, still it will take 180 seconds only because we have coded it like that. Let's wait for this much time and we'll move further. Only 10 seconds are left. In this conventional mode, user can set the temperature up to 180 degrees Celsius. Here includes the preheating. Now here we have to again set the time. Let's set it as 5 seconds and it will finish. Uh, okay, cooking time up as we are getting. And now last mode is start mode. Here nothing, we have to click start and it will set the time. Oh shit. Okay. Let's set the time of 30 seconds and within a single button press if you want to do something cooking. Let's revise everything. In micro mode, user sets the power, which is default, and time, example 15 seconds. The fan rotates to simulate heating until the timer hits 0. Second is grill mode. User enters the cooking time directly. Similar fan operates during the countdown. Third is conventional mode. User sets the temperature up to 180 degrees Celsius. In this mode, only difference is there is a preheating phase, like it was 180 seconds here before the actual cooking starts. After the 180 seconds, we can set the timer. And last one is the start mode. Here is a quick start button, which if we click, There is a 36-second timer. That's it. We have learned all how micro oven works.